Thank you very much for that introduction. It's a great pleasure to be here and to continue perhaps where Bernard left off this morning. I'm going to overlap a little bit with some of the things that he has said, but I think that that will be all right. So I'm going to talk about cosmology, and in particular, I'm going to talk about first cause arguments. But we'll first of all have to just skip a bit through the history of how things developed. So here, as you saw, is a picture of the medieval universe, which was based on ideas of Ptolemy in the Roman world, and the Earth was at the center. There were concentric spheres revolving around that, and on the outside there was a sphere that enclosed the stars, and beyond all that there was the celestial sphere, and that was the dwelling place of God. And it was a finite system, and everything was very well in its place. Now, Newton, skipping a lot of time, had very different ideas. He said that the universe must be infinite, and his reasons were as much theological as anything. He thought that God has to fill the universe, and God is infinite, so you have an infinite universe. He felt that matter is in principle spread out everywhere, but then it clumps together to form stars and planets, which is not so very different from the point of view that has been developed over the years since then. And one might as well add that Aristotle denied that physically infinite things could exist. So Newton and Aristotle are certainly in disagreement on that issue. So during the 19th and early 20th centuries, it became recognized that the Earth is very old. Now, this is the Earth to start off with. Geology was the key science. People looked at layers of rock, and they decided that you just had to have a very old Earth. People debated about this. But nevertheless, a lot of scientists thought that the universe was still infinitely old. Our Earth just came about at some time. And this was discussed a little bit this morning. And it became recognized that what were called nebulae were actually galaxies just like ours. I won't talk about the steady-state universe. This was proposed in the 1950s by people who didn't like the idea that anything really ever changed with time overall. It was based on a philosophical principle that things were always the same, and it was a philosophical assumption. Well, there are two particularly important developments in cosmology in the 20th century, and one has been referred to in passing, Einstein's theory of general relativity. Now, for those of you who aren't physicists, this is a theory of space and time, and it relates the properties of space and time. So space and time have properties, and it relates these to the density of matter, energy, momentum anywhere in space, which are the sources of what Einstein developed as a curvature theory of space and time. So you can have a universe which is sort of curved round on itself, but it doesn't have to be. Now, at the same time, Hubble, who you heard about this morning, analyzed data concerning how fast galaxies and stars were moving from us, mainly galaxies, and he found that the further away a galaxy was, the faster it is moving away from us. So this he put together and said there's a constant. Well, it's not necessarily a constant, but it's now called a Hubble parameter, and that tells you the rate of expansion of the universe. How fast it's expanding if you look at things at a particular distance away. And after that, in the 1960s, as you saw, there was the discovery of the cosmic microwave background. Now, this is another picture of the expanding universe. Because if the universe is expanding, you can do some calculations, and you find out that it looks as if at some point at a finite distance in the past, it was all at one very small point, or something like that. And after that, everything has just been getting bigger and bigger and bigger. So this point where it all started is referred to as the Big Bang, and it's basically space that has been expanding as the years have gone by. This is a picture of a sort of finite spherical universe. We don't know whether the universe is finite or infinite. We maybe never will know whether the universe that we live in is finite or infinite. But as far as this pictorial representation is concerned, we're just thinking of it for convenience as something that might be finite. And it is the space itself that is expanding. It's not really true that a galaxy many light years away is moving away from us particularly. It's just the space between us and it is getting bigger all the time. And what we now think of as the cosmic microwave background, this is very low energy radiation. At the beginning of the universe, it was very high energy radiation because energies were higher than then and all the distances were smaller, wavelengths were smaller, and this was a very hot period in the universe. Here's a cartoon. Einstein in 1929 began to convince himself that people were understanding his theory. They said people would slowly accustom themselves to the idea that the physical states of space itself were the final physical reality. Here are some people in New York accustoming themselves to that idea. And since then, quantum fields have been introduced, and I think they would have been even more puzzled if they'd had to think about that as well. Now, here is the history of the universe on one slide. The Big Bang, followed by everything else. I'm going to take you through this briefly so that you can understand the picture that's being presented. So, start off with the start of the universe. Big question there. We'll talk about that later. But this is something which people argue about quite a lot. We don't really know what has happened then. Then, immediately after that, it is supposed that a process called inflation started. This suddenly means that because of quantum fields in the universe started to expand very, very quickly, and then it stopped when it was a certain size. So this is like 10 to the minus 35 seconds after the start of it all. That's a pretty short time, but that's what is worked out. Then it stops. Now, at this point, I have to say that there's argument about inflation. Not everybody accepts it. There is good reasons to believe in it, but also the theory has not yet been fully made to work to everybody's satisfaction. There's a fellow called Paul Steinhardt in, I think it's Princeton, who is very skeptical, and he's made his view clear that the theory, he thinks, has not yet been brought to a proper mathematical state. It's a bit out of control. Anyway, just to take a note that this is commonly believed and may be true, but there's still work to be done. And it stops when the universe that we can observe is 10 meters in diameter. So it would fit in this room. Then particles, quarks, gluons, and various things start to form. This is not fully understood, but that is when the matter that we know about begins to form. And after that, after 3 seconds, all the protons are now formed, so it's believed. And they can stay as protons, they can become neutrons, they can form matter. Now, it's believed that this is really the main source of protons in the universe. Now, in our bodies, there are lots of protons that make up water, for example, H2O. So the protons that we're largely made of probably date, in the main, from 3 seconds after the start of the universe. Then, after 400,000 years, you've got stable light atoms. Now, before then, photons were bouncing around all over the place. But after that, the photons stopped being absorbed and bouncing around. They just sort of propagated through space. And it's these high-energy photons which just lost their wavelength as the universe expanded and now are looked at as microwaves. So that's how much the universe has expanded since those early days when everything was very hot. 400 million years, quite a skip forward, hot, heavy stars form. Now, these first stars are very important because they went through their hydrogen and their hydrogen fuel very quickly, and then they exploded. But in that process, a lot of nuclear reactions occurred, and these nuclear reactions generated heavier elements. I mean, heavier than, let us say, lithium. So carbon, oxygen, all the elements that we're made of got formed by these heavy stars in the main at this rather early stage. And the universe became full of debris from these exploding first-generation stars. Then, 1,000 million years, things start to condense into galaxies, the sort of picture that Newton was trying to portray, though he didn't know about galaxies. And we can observe back to this point, except that the cosmic microwave background, we can observe back further. So that's why the cosmic microwave background is so important, that it gets us back further than we can observe with our telescopes, even radio telescopes. Many millions of years, we get more and more happening, smaller stars and planets, heavier elements, planets like the Earth, and so on. 8.7 billion years, I'm sorry about the destruction there, our solar system formed, so we work it out. And finally, we are here today. So that's the history of the universe in a nutshell. And that's what you need to have in mind from what I'm going to be discussing next. So having got that picture, we're going to have a bit more of a theological part of the discussion. And I'm going to introduce you to what is commonly called the Kalam argument for the existence of God. It's Islamic. It means the scholar's argument, and it dates from the period I've indicated, 9th to the 11th centuries AD. And the simplest form says that anything that comes into being must have a cause. And the universe has come into being, so it must have a cause. And this we may naturally identify with God. So that's the simple form of the argument. You can generalize it a bit more. You can say, well, causes are a very important general thing. The state of any physical system surely needs to have a cause. And you may need to use a more general form of the argument at some point, but that is the basic argument. And it means that you do have to believe in causes. And this is something that our first speaker stressed as a very important part of the way we think and the way, indeed, that we operate science. Now, this, not surprisingly, has been contested. Not everybody likes this conclusion. But amazingly, I think it can be said that most people agree that the basic Big Bang should have a cause. The argument is in practice accepted. But what should be the cause? If you don't like the idea of God causing the Big Bang, our universe, then you've got to have a physical system that existed before that, a prior existence for the physical system. And so the question is, could this go back indefinitely? If it could go back indefinitely in time, you might be able to say there never was any point where you could talk about a first cause, and you could try and avoid thinking about a creator. Now, this is an argument that is widely acknowledged as having some weight. Now, Stephen Hawking, who is not particularly sympathetic towards normal Christian belief, or any other as far as I know, says a point of creation would be a place where science broke down. One would have to appeal to religion and to the hand of God, and it's not something that he is particularly keen on. Now, what I'm going to have to do now to consider this in more detail is take you through what I believe are the most important ideas that have been put out by cosmologists in recent years concerning the possible pre-existence of a universe, which I'll try and refer to as a cosmos. So, as we said this morning, let's think of a Big Bang structure as a universe and something more general as the cosmos. And this will get a little bit technical, but this stuff does get into the popular scientific press. You will certainly read about yet another idea that somebody's had which might get around the first cause argument. So I'll try and give you a non-mathematical outline of what the cosmologists have been saying in recent years. And first of all, two things to mention. There's a theorem, and this is called the Borda-Guth-Vilenkin theorem, dates from 2003, so that's relatively recent, a fairly recent development. And it basically says that if things have always been expanding, there must have been a beginning, even if your cosmos is more complicated than a simple universe. They do a mathematical calculation. They say if the Hubble parameter, which is averaged over all past times, is positive, in other words, things have always expanded, then the cosmos must have had a beginning. And nobody has really got around this. It's to do with the speed of light. Now, there are thermodynamic issues, which I won't say anything more about, but it is difficult to have an infinitely long expanding universe with things happening all the time without having the universe just run down and look featureless. There are problems with an infinite age to an infinite universe, says Aaron Wall, an infinite number of causal events in a finite universe, but to digest this properly, you have to digest his paper, which I must say I haven't yet fully done. Now, what are the options? Well, we just mentioned a simple Big Bang. We don't ask what happened before, nothing happened before. Well, in that case, the Kalam argument would presumably apply. If you believe in a general principle of causation, something other than physics must have caused it. And you may naturally say that this was a creator of some kind, God, presumably. But people have argued that perhaps the universe oscillates. In other words, it gets bigger until it reaches a maximum size, and then it contracts down again. That's called a big crunch. And it keeps on going like that indefinitely. It has been doing this indefinitely. So no beginning to anything, it's just the way things are. Now, this has been analyzed in more detail, and it's found that you can't really set up easily a stable set of oscillations which keep on going in exactly the same way. Two things happen. One is that the universe eventually goes into permanent expansion. Well, our universe, it looks as if it's expanding permanently now. This is, again, a modern development. People have analyzed properties of galaxies and supernovae and things like that, and we now believe that our universe will expand forever. So if it were an oscillating universe, that means that we're in the first phase when this is happening. What amazing luck. That's pretty improbable, and there's no particular reason for this. So that makes you suspect that this just isn't the right model. And on top of that, you find that if you trace it back in time, these oscillations get faster and faster, and it actually had to have had a beginning. So this will not get us off the hook, and it's probably not the right model anyway. Now, let's talk about something which certainly remains a popular idea, so-called internal inflation. Now, the idea is that this inflation process is, in fact, the basic thing that's happening everywhere in the cosmos. There's a field which makes everything expand violently. But every now and then, there's a sort of, like a pop, and a sort of normal universe materializes. These are called island universes or pocket universes. And within this, ordinary space like our own occurs, and our own universe is one of these. There are lots of them. How many is a good question, but the idea of this doesn't determine this necessarily. Now, the thing is that the BGV theorem, which I mentioned, actually implies that this must have had a beginning. No violent expansion, it must have started. So whether or not you believe in a multiverse or this kind of internal inflation scenario, it looks as if the mathematics implies that it started at some point in time. Now, the opposite extreme is to suppose that somehow or other the universe had an eternally uneventful past. It was just sort of sitting there for an indefinite amount of time, and then it decided to expand, and you can put flesh on the bones of that argument. Now, people look at this, and there are problems there too. It's very difficult, it seems, to make this sort of model give you a stable universe. I mean, something that will stay stable for an infinite amount of time. That's a long time to be stable. So if there's any kind of instability at all, that will happen. It could contract to a point, collapse, or it could have already done something like expand. Why should it have waited for an infinite amount of time before doing something now? So these ideas, there is a general feeling, as far as I'm aware, that it's very difficult to make them really work. Now, Hawking and Hartle produced a famous model, and that's mentioned in Hawking's first book, so we have to at least consider what he's saying. Now, he says that it's not true that as you go back to the very beginning in time, there was a point where things were infinite. That's a so-called singularity. He says that some time very close to that, before then it was different. There wasn't any real time before then. It was something he called imaginary time. This is a mathematical construction. Imaginary time looks rather like space. But his idea was to sort of round off the start of the universe so that it was all very tidy and mathematically well-defined. But if you really ask what's going on there, and it's a very ad hoc assumption, I don't know that there's any real reason for believing this other than mathematical tidiness. You still have to ask, well, causation can only occur in real time. The imaginary time, presumably, isn't like time. It can't have causes in it. It's just a structure. So what caused all that to be? If that, too, you have to ask, surely it needed a cause. And so you still ask the same question as before. Now, I've put as the sixth suggestion, everything emerges from a quantum object. That is a completely general idea, because nobody really knows what the quantum object would be, but since we believe in quantum things and we don't yet know how to quantize gravity, it's quite a plausible notion, even though it's not exactly a theory at present. Indeed, maybe that's exactly what happened. We still then need to ask what is the cause of the quantum object. So again, you have the same question as before. Now, let's go to a book which came out by Lawrence Krauss, who is well known for being sort of anti-religious, A Universe from Nothing. Now, most of his book is a description of the Big Bang and physics and cosmology, and it's very good. He explains these things pretty clearly. And finally, at the end, he comes to why I think he really wanted to write the book, because he thinks that you could have a universe, as he puts it, from nothing, not even a question mark. Now, it's not very clear what he's really proposing, but he seems to be saying that quantum fields can fluctuate into a proto-universe, and then it all takes off and you get a Big Bang. If that's what he's saying, it's not nothing. It's clearly something. You need to have some sort of prior existing space of some sort, you need to have your quantum fields. So he has rather misled people, but he seems to be implying that it really is nothing. Now, of course, if you really wanted to say that the universe appeared from absolutely nothing, you can't reify nothing. It's just not there. All you could say is that the universe had a start at some point. That's what a real philosophical nothing is, that there just wasn't anything there before. You can't come from nothing because it's not there to emerge from. So one has to be quite clear here that if somebody really is saying that the universe came actually from really nothing, they're just saying that it had a start in time. That's all they're saying. There's nothing more than they can say. It could be that the medieval philosophers expressed themselves a little bit badly here, because the phrase ex nihilo exists in classical descriptions of creation. What it really means is that there wasn't any prior existence of material that God created the universe out of. It just started. But that's by the by. So we haven't yet found a way of really making the infinite past history of the universe idea work. And that does appear to be the current state of thinking on the whole. I could make a few more comments here. Now, general relativity is a very flexible mathematical theory. And, I mean, we believe in it. It's been tested in various ways, not completely tested out, but as far as we can tell, all the tests that have been done, general relativity is probably true. With a, it might turn out not to be, but it looks to be okay right now. And it allows you to stretch time if you want to, or space. You just have a different set of equations. The usual idea is that you choose whatever space and time description will simplify your argument and your calculations. So they do this all the time. They say, I'll go to a different frame of coordinates because this makes that calculation easier or less difficult. Now, so if you really did have an infinite amount of time going back into the past, as far as general relativity is concerned, you could just transform that away so that an infinite amount of time became mathematically transformed into a finite amount of time. Now, this is a tricky thing to argue, perhaps, but it may well be that it's very difficult to talk about an infinite past time in a hard and dried way anyway, because you could always rephrase it, as it were. And then, of course, there's the old question of whether it's legitimate to talk about a physical infinity. Now, this is a very, very tricky point, which people have always argued about, but you should remember that mathematics and physics are not the same thing. In mathematics, you can formulate ideas any way you like. You can say, well, I'll start off with a finite physical system, and I'll just see what happens if it gets infinitely big. You can do all that mathematically, and the mathematics of infinities has all been worked out to people's satisfaction. Whether you can actually start off with something infinite and say that's the physics is, to say the least, debatable. It may be possible, it may not, but there is a question there. And what this really means, I think, is this, that if somebody just sits down in an armchair and says, oh, it could be infinite, they ought to be challenged. Infinities are not to be played around with loosely. You've got to be able to justify whether the kind of infinity that you're proposing is mathematically sensible, whether it's physically sensible. If you don't do that, then you haven't really said anything concrete. So all of this in practice is, as I say, difficult to deal with unless you're prepared to think very carefully about a particular proposal. So general statements, oh, it could have been infinite, are not really legitimate these days. So this takes us through what I believe are the main cosmological theories. There are some more. For example, there's an idea that the universe might have contracted down to a small point and then expanded again, but time went backwards when it was contracting, which is another way of saying you have two universes both expanding but joined together. You have the same problem again. What happened to cause the event at the point where these two universes emerged from? So it does appear, as I say, the Kalam argument holds right now, and you therefore, if you believe in a strong principle of causation, an extra-physical first cause is implied because we've dealt with the physical possibilities that we can think of. Now, yes, a word of caution from Leon Lederman, author of the God Particle book. So you can read that. That's his opinion, and I think it's probably an opinion that quite a lot of people would have if they're not cosmologists, that we are not in the realm of experimental science, really. There have been some sort of ideas that you could try to test it. At present, we don't really know how to test any of these ideas. So there's an issue here, whether this is philosophy or science. It might turn into science once you can propose some good experimental tests. And I think one should also say that the Kalam argument is largely directed towards physical materialists who might not wish to believe in non-physical causes. Now, if you have a religious faith, you believe that God is there, and there's a perfectly good way of thinking which says that God causes everything all the time. I'm not arguing against that. Of course, the beginning of time is part of time. So you're not excluding any other theological points of view by pointing out that it looks as if the purely physical picture isn't sufficient in itself. And I have not said anything against what you might call spiritual causes. If you believe, for example, that God is able to interact with people and do things from the heavenly realms, that has nothing to do with what I've been talking about. It's something that you're perfectly allowed to believe in if this is part of the faith you have. So that's, again, not something to do with this particular argument. And if you want to read what I've said in more detail at length, last year I published a longer version of this in the journal Science and Christian Belief. And you can turn to that and read it at your leisure. But since I've got a few minutes left, I think I'll go on to talk about a few more things. Well, first of all, final comments about this. I have said nothing about the nature of the physical laws and constants. This was alluded to by Bernard, and I'll say a little bit more about this in a few minutes. So, although I've said here another talk to deal with the subject in detail, I will just reiterate some of the things that Bernard said this morning. Now, there's always a general caveat. The science can always change. People have had these ideas about cosmology, which I've outlined. It could be that next year someone will have a really brilliant, creative new idea which will change the situation. You can't say that this won't happen. So this is how it is right now, and this is the state of the argument. And you must believe in causation. I've stressed that. So although you can believe in God without believing in a first cause, because even if the universe were infinite in time, you still could very well ask, why is it there at all? And you can say there should be a general reason for even an infinite universe to exist. And some sort of creative being is clearly something to bring onto the table at this point and say that you believe in God who can create anything with any structure. I've not, of course, been able to say anything about the nature of the first cause from this argument. You can't say from the Kalam argument that it must have been a personal God, it could have been a deistic God, whatever. In fact, some of the skeptics might well, if you drove them into the corner, say, well, you know, perhaps there's a distant deistic God. But their thing then would be not really wanting to believe in a personal God. So now, since I was originally asked to say something about multiple universes, I'll spend a few minutes doing that. But let's just go through again about why, one reason why one might want to believe in this. As Bernard said, you've got to form a universe for human life because we're here. And that means that it must have been possible for us to be here. And so you ask, what's on the shopping list? What would you have to make a universe which is suitable for beings such as ourselves? And 3 space dimensions are important. If you have more than 3 space dimensions, then gravitational orbits of planets around stars won't be stable. This can be worked out. You can do the calculations in multiple dimensions. 3 space dimensions give stable planets, and that seems to be a good idea. So I suppose if you believe in string theory, there may very well be some structures out there with 7 space dimensions. I'm not saying I believe this, but there could be, but they would not form planets the way that we have a planet. You have the various nuclear forces, electromagnetic force, weak force, gravity. And here is a picture of all these elementary particles. They also have antiparticles. I won't go through all this. Quarks, it's the up and the down, the U and the D quarks that make up matter that is stable. The rest are unstable. You have to make them in elementary particle accelerators and spot them by what happens as they quickly decay into other things. But we have reconstructed this picture by looking at all sorts of different interactions that can take place in particle accelerators, and this is what comes off. And the blue symbols on the right, the gamma is a photon, G is a gluon, that's the strong force. The Z and W convey the weak force. The weak force is responsible, for example, for radioactive decays of a lot of elements. So uranium takes a long time to decay. Well, perhaps that's not a very good example. Let's say carbon 14 takes a long time to decay because it's the weak force that does this. But it can act quite quickly, but it's not as strong as the others. And the Higgs particle is a final piece of the mathematical jigsaw puzzle. Now, this, I hope you'll be prepared to believe me, is a mathematically complex and subtle scheme. This is why it took so long for people to work it out. It's a very cleverly, ingeniously set up system that enables all this to happen. And here is a lot more requirements for a universe, for human life, some of which you saw this morning. You must have more matter than antimatter. That probably means that you've got to have more than just 2 quarks when you work it out. The others give you more flexibility in the forces to generate an asymmetry between matter and antimatter. The universe must be long-lived, which puts various constraints on the parameters of the universe. You've got to have it something like, well, let's say 10 billion years, 14, whatever we are occupying, it's got to be that order of magnitude. 1 billion years probably wouldn't be enough. You've got to form galaxies. You've got to form hydrogen, but the right amount of hydrogen. If everything was hydrogen, nothing would work very well. But if nothing was hydrogen, it wouldn't work either. You've got to have a suitable amount of helium because the heavy elements get formed out of helium. All that has got to be got right in the early stages of the universe. I could put numbers in here, but we don't have time today. you've got to form heavier elements in stars. Now, that's a tricky one. It's not so easy as you might think to get exactly a really good amount of carbon to be formed, because we're made of carbon, and so on. The first stars must explode properly. You must have a suitable mixture of stars. Some, like our sun, others are big and powerful. Organic chemistry. So all of this puts a lot of constraints on the kind of physics that you have. And yeah, there are possible explanations. One is the fine-tuning is naturally unlikely, but God made it happen. That's entirely reasonable from a believer's point of view, and it means that there's purposeful design. It's intellectually a perfectly good idea, but it does mean that you've got to give up some of the other ideas, perhaps. Just by luck, the only possible universe is anthropic. Well, that's hard to evaluate, but you do require a lot of luck. Multiverse. Okay, now there could be many, many universes. And then the idea is that they've got to have different properties, and we live in one that's good for us. It's perfectly possible to have one huge cosmos with lots of universes in that are all the same. Why not? It just means that the constants of nature are always all the same. That wouldn't solve your problem, of course. So you've got to have a particular kind of multiverse with a lot of variation in all the physical constants in order to get this kind of randomization process working. And superstrings have been proposed, or M-branes, as was mentioned. Now, the thing about M-brane theory is that it's not actually a theory yet. It's so complicated that people think that they ought to be able to work it out, but it hasn't been done yet. So one is jumping the gun a bit by saying that here is a theory that will explain everything, because it's not yet there. But you can have lots and lots of quantum vacuums. Now, quantum vacuums just means the sets of parameters and physical laws of nature and numbers that do things. 10 to the 500, probably enough. One doesn't really know. But you can model the number of universes separately. I mean, the number of different permutations of superstrings is one thing. How you actually form a universe is another thing. So you've got two different problems to work out. Now, Penrose, you've heard of Penrose. He has the following objection to a multiverse. He says that our universe is unnecessarily large for our needs. We could live in a smaller universe, let's say a tenth of the size. He's probably right, I suppose. But then he works out what he thinks is the likelihood of a large universe appearing, and he says that most universes are much rarer if they're large than if they're small. In fact, he believes that if the universe were a tenth of the size of ours, there'd be hugely many more of them. In other words, we're living in a quite fantastically unlikely universe. He calculates this factor as 10 to the 10 to the 1, 2, 3, which is a preposterously large number. So if you believe his argument, you have to believe that for no good reason, our universe is much, much larger by far. A very, very rare event has happened. Well, it's a matter of judgment. Now, of course, we can always allow God to create universes, many of them. And this was suggested years ago in Europe, that God could create many universes. In the Middle Ages, the Archbishop, or was it the Bishop of Paris, said in a number of pronouncements that you should not prevent God from creating many worlds. Perfectly possible. You mustn't limit God's power in this way. So this has been on the table for quite a while. But you still need general laws of physics, of course. And I think one should say that you shouldn't dumb down God too much, because the mathematics of superstrings is, well, formidable. It's too difficult for most people. It's probably too difficult in real detail for anybody. Even Ed Witten, who is probably the most brilliant mathematical physicist alive, I think there are things that he hasn't worked out yet. So this is a big intellectual requirement to get these superstrings right. What observational? None really. There was this idea that there's some feature of the cosmic microwave background might be an indication of another universe. I think people aren't talking about that so much right now. It's debatable. So with that kind of questionable assumption, we don't have any evidence for any of this. And how could you actually test the ideas? One doesn't know, really. It might happen. One can always imagine that what is now philosophy will turn into science when people think of some good experimental tests. So why should you believe in these theories? Well, philosophical reasons, you like it. Aesthetic reasons, you like it. Anti-religious reasons. Now, the people who put these theories out always say that their motivations are A and B. But, well, I don't know. Oh, here's a bit of popular journalism for you. The people who put out this edition of the Scientific American were clearly completely convinced by the cosmologists that it was absolutely definite that there were lots of parallel universes. Well, who knows? I don't think this was a particularly scientific example of this normally very reliable journal. Okay, Max Born, he became a professor of physics at Edinburgh. He was a well-known quantum theorist, and that is what he had to say about things in general, that a certain amount of common sense, if you can rely on that, might be a good idea. So that's just something to think about. That was his opinion. Oh, finally, human specialness. This, we come back to Bernard's point that, no, we are conscious beings. We have consciousness. I have, and I presume you have too. Physics doesn't know how to deal with this. Complexity, with all respect, has not actually given us anything other than a pre-requirement, perhaps, for consciousness. There's something more coming. So you need an anthropic principle if you think that physics is preparing the way for something which is non-physical, because why should it do that? If you don't believe that there's anything special about us, then you could just say, okay, it's just the way it happened. It could have happened in innumerable other ways, no need to explain anything. But it seems that there is something here that does need to be explained. And, well, we could accept that the universe looks designed and just accept the theological consequences. Well, unbelievers would say this is wishful thinking, but, you know, there is evidence. I don't say it's proof, but it's evidence that this could well be the case. There also exists, as Bernard mentioned, a reluctance to believe in God from unbelievers. Susskind, who wrote a book on the cosmic landscape, all about superstrings, that's what he said. The anthropic principle, he says, makes many physicists very uncomfortable. Need for a supernatural agent, threatening, anti-scientific idea. Well, it's very much, I would say, a personal and emotional feeling, but it's one that a lot of folk probably have. And you can't just sweep that under the carpet while accusing believers of having other motivations. I think that probably most people have a lot of background dispositions to believe different things. Well, let me give you my personal views here. This is just one page of thoughts. I think I am basically agnostic about a physical multiverse. I don't know. Maybe there may not be. I'm reluctant to believe in a very elaborate theory without good observational reasons, though. So I am, in fact, suspicious of violating Occam's razor, which says you shouldn't have more things than you need so extravagantly. There's also a basic philosophical principle of science, let's say. If you have too many universities, especially an infinite number, you can explain anything you like. Anything you think might exist somewhere will exist somewhere. And does this trivialize science? you've got rid of nice, tidy explanations for something. You've just said, well, we're in the universe where that one happens. And one should be a little bit wary, I think, of this. We haven't talked about the many worlds interpretation of quantum mechanics, but I just jotted down that for reasons I can justify afterwards, I find that very implausible. So here's a statement, and it's a warning about getting too intellectual without putting some observational flesh on your argument. T.H. Huxley in 1890 was speculating about a sort of scholarly, civilized religion of the future. He said, no longer in contact with fact of any kind, faith stands now and forever proudly inaccessible to the attacks of the infidel. And I think that cosmologists need to be a little bit careful that their subject doesn't drift too far in that direction. So, thank you very much.